On this episode of This Week in Space, we're talking about dark matter and dark energy. So join us and come into the light.
Podcasts you love.
From people you trust.
This is Twit.
This is This Week in Space, episode number 118, recorded on July 5th, 2024. Understanding the Darkness. Hello and welcome to another episode of This Week in Space, the Understanding the Darkness edition. I'm Rod Pyle, editor-in-chief of Ad Astra Magazine, and I'm here with our honored guest co-host, Isaac Arthur, president of the National Space Society and creator of Science and Futurism with Isaac Arthur. I'm not sure which one's a bigger achievement, Isaac. I think your channel is probably a bigger achievement.
Well, it's the one I get to spend the most time on and personally love the most, but I love the National Space Society and getting to be its president is just amazing. So it's getting right for Ad Astra, too. So it just came out to me.
Please do. Please write for us as often as you want. And I probably will find a way for your presidency to end up taking up more time than your podcast. That's another, not a podcast or video channel. Sorry.
A show.
Our guest today, we're going to be talking about dark matter and dark energy, are Alina Kiessling and Jason Rhodes, who are both research scientists and astrophysicists at the Jet Propulsion Laboratory. And just saying those two phrases together makes my brain hurt, because I took just enough astronomy at UCLA to discover that I should not be an astronomy major and I should not try and be an astronomer, because if anything, I was going to end up being somebody's flunky and they were going to be doing all the cool stuff because
I told my grad advisor now. He talked to me about going to astrophysics too. So,
yeah,
you don't want to do that. You'd be in charge of the vacuum tube or something like that. So I kind of regret that at times.
Yeah, I didn't even get to the graduate advisor. It's just like
fascinating field.
Third year, it is, and especially if you're at a university that's got an observatory you can use, which is pretty cool. But that was a long time ago, and I've forgotten more than I learned, which I think is a net negative. But anyway, I guess you can do that if you pick. Okay, before we start, please don't forget to do us a solid. Make sure to like us, subscribe, and all the other cool podcast stuff. We're counting on you. And just to show how much we're counting on you, I'm going to alienate you now all with a space joke. This is from Up Joke, that's not a good week, but nobody sent me a better joke in email, so I had to resort to Up Joke. Along with antimatter and dark matter, we've recently discovered the existence of doesn't matter, which appears to have no effect on the universe at all. Oh, the canned audience loved it.
Awesome.
Or it ain't love that binds you to your partner, it's dark energy. Okay, thanks, John. Hey, save the cosmos from our humor, although I didn't mind that one too much. And send us your best, worst, or most different space joke at twis@twit.tv, and we will read it and we will credit you because you're the listener and you're the most important thing in our universe. All right, let's get some headlines. So this first one I've entitled Oops and Up, because last week, a Chinese rocket startup called Space Pioneer, which is a quasi-private public government sort of a enterprise, launched a rocket by accident. So if anybody ever saw the movie Space Camp, you know what I'm talking about. They were doing a static ground test and just powered up. Everything was going fine. And suddenly off went the rocket. And they found in a post-mortem examination that the hold-down brackets, not the clamps on the pad, but the brackets of the rocket had failed. And fortunately, it flew over a nearby village into the side of a mountain. But it's always bad to have unintended launches of your rocket. But nobody was hurt. The rocket, by the way, is called Tianlong, which is Chinese for flying dragon, which I thought was an apt description for a rocket that takes off if you don't intend it to. Did you see this story, Isaac?
I saw the video on that. And on one hand, I'm kind of sympathetic because when I was 8, I was building Estes rockets. It was the last one I ever got to build because it went off inside the house. And nothing was damaged except this one little plastic yellow chair I had this giant scorch mark on it for years.
Okay, now wait a minute. For that thing to ignite, you have to proactively put an igniter wire in it and hook it up to an ignition
it went
source.
off on its own, and it was just sitting there by itself. I don't know how that happened.
I was just sitting there, and the hatch just blew, right?
Yeah, it just blew. So I guess these things can happen, but that was the end of my model rocketry days, it turned out. On the other hand, I saw that explosion going out there, and I was in artillery in the Army for years, and I've seen big explosions. Rockets go boom, and I find myself a little dubious about the no one was hurt part, but it does, at least thankfully, many miles from the actual town itself. And you know, this is rocketry. It's hard to do. Accidents, weird things happen. Stuff does blow up on the pad a lot. But, you know, hopefully we won't have a recurrence of that.
I'm still stuck on I was playing with my model rocket and it just suddenly ignited all by itself. Maybe we got to put together with you guys. You could compare stories and come up with a good
I was a pyromaniac as a child and adult, so I don't know, but I don't recall doing anything that it went off on its own. It was in the sun that could have potentially done something. I have no idea. 1980s designs, small one. But I like that chair afterwards more because of the scorch mark.
I can't tell you how many times I've read from both Estes and Centuri rockets. Our engines can never go off spontaneously, but hey, whatever story you want to stick with is fine. Okay, let's move on to Polaris Dawn. So SpaceX and Jarek Isaacman, our favorite space Jesus, have targeted July 34th for the first flight of 3 of the Polaris Dawn series, which is very exciting. And this one, so they've already done one, which was a charity flight, which is very cool. And they had an observing bubble on the end of the capsule. But in this case, they've got a hatch up there and they're going to do the first private spacewalk in history. That's going to be somewhere about 400 miles, which is a little under double the altitude of the space station. But then they're going to go for an orbital record of 870 miles in altitude, which is actually a little higher than the highest Gemini flight, which is Gemini 11, which I think was 853. So the only crews that have flown higher, quote unquote, or further than that have been the Apollo crews. But this is actually up dipping in and out of the Van Allen belts, which can be highly radioactive. So that's going to be an interesting flight. They'll do a lot of good science. So aside from Isaacman, the mission includes retired United States Air Force Lieutenant Colonel Scott Kidd Poteet. I guess you have to be in the Air Force to have a nickname, right, or a handle. So it's Kidd, K-I-D-D. And mission specialist Sarah Gills and Anna Menon, both of whom are SpaceX operations engineers. So this is pretty cool. Now we know if you get a job at SpaceX, you can possibly fly on a private mission. Finally, they're going to be testing SpaceX's brand new EVA suit. They've had pressure suits for years. You've seen them. They're the sort of interesting, slightly goofy, superhero-ish pressure suits they have with the tall boots and all that. Now they've designed from that an EVA suit, and that's another one of those things that sounds easy but is not. So what do you expect, Isaac?
I was trying to remember if they do those ones as partial pressure or full mix. So it's a hard choice on those, but I'm worried about the Van Allen belt. Always seems to be a great chance to do science, but it should be a good chance to actually see what a new spacesuit can do in a real live test, because we've been trying to improve those things for years. We have made many improvements to them over the years, but it is one of those key pieces of technology for places like Mars or the Moon, or just even doing maintenance on spacecraft. Yeah. If you can't get a good spacesuit that can keep air in and keep people alive without feeling like you're wearing 5,000 pounds of padding, you're not going to get a lot of real work done in space. And you and I both know from talking to astronauts, wearing a spacesuit is like living in a sauna, only smellier and scarier.
Well, and especially when you look at the International Space Station, where the spacesuit components were built in the 80s. Yeah. That's a long time ago. And there's plenty of people listening to the show that weren't even born in the 80s. And these spacesuits predate them by 10, 15, 20 years. So it's time to come up with a new design affordably. And of course, Axiom's working on that for NASA, but as usual, SpaceX took the bit in their teeth and ran with it.
It is a great example of how space tourism can actually come back to benefit on the science side. Is one thing that, going and floating in space for a couple minutes in a bubble is going to be nice, but to actually get out there in a suit is what people really want. Yeah. And when you're building 3 or 4 spacesuits a year tops just to be used in space, that's never going to get you all that real level of engineering you want. We are manufacturing dozens of them because you actually had that many space tourists going up there who want to be able to put their hands outside, who want to float free in space with just the visor there. That means you start seeing real, genuine improvements by people who can complain about it more, And I think that is a good positive sign and an example of how space tourism will be able to benefit the space community in general.
I should mention these are EVA suits, not lunar EVA suits, and there's a big distinction there. So the job that Axiom has been charged with is actually much harder because when you're doing orbital EVAs, you're not worried about dust incursions on your cuff seals and all that. So for a lunar suit, much bigger deal. All right. Finally, a Starlink update. That should be Starliner update.
Yep.
NASA announced the Starliner is in good enough shape to stay at least 45 days. Golly, it was only supposed to stay a little over a week. It was originally envisioned maximum stay at the ISS. While NASA says it's safe enough for a crew to return if needed, if absolutely necessary, at any time. Ground testing of the malfunctioning thrusters continue, and investigations into the helium leaks continue. And at this point, the helium leaks tend to have stopped for the most part, appear to have stopped for the most part, but it's still an area of concern. Another area of concern, the spacecraft batteries, which is one of the things that limits how long it's supposed to stay at the ISS. But at this point, they're charging up from the ISS. So the core line of this memo is no worries. The astronauts aren't stranded. Starliner's fine. It's just going to stay a little longer. And then, of course, the press conference, the press says, how much longer, NASA? And they said that is undetermined. So we've got this kind of mixed message of everything's fine, but we don't know when we're bringing it home because it's not working properly. Huh?
Nothing to see here. Everything is good.
Well, a little bit, and it's funny. I as I mentioned, I think last week, I had posted a couple things on Facebook and a couple of other places, pretty neutral about Starlink, a little snarky. Starliner, a little snarky perhaps, but boy, it's like touching that third rail. You suddenly get a lot of response, people saying, it's harder than you think, and Boeing is great, blah, 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 blah. And, that is probably to some extent true. It's just that some company like SpaceX, for whatever foibles and failings they've had over the years, just from the casual layperson point of observation, it makes Boeing look like they're standing still. And the other thing I cannot understand is how this has been such a challenge. And yet SLS, which was expensive, and that was done on a cost plus contract, which this is not, this is fixed fee in theory. But SLS works. It took a while, but so far it works.
I guess I'll play devil's advocate for them a little bit here. You're very right to point out that they look like they're standing still when the ship's been standing still for a while. I was always making fun of the James Webb Telescope about when it would get launched and how it eventually got launched. And once it actually did, we all forgave the huge timeline delays on that. And I would say it's you don't really want to have a monopoly on spaceships. You want to have multiple companies in that window, and that means they're going to have because not always going to be exchange trade secrets. Of course, you're going to have people trying to get into that ecology that are going to make mistakes and have their own fair share of mess ups along the way. Some might be a little bit more embarrassing than others. At the moment, this is the kind that is humorous, but everyone's alive, everything's working. And that's what we like about space is the amazing non-lethality of space so far is always one thing to be impressed about. Nobody's dead, no one's injured, and that is always in its own right really impressive. So,
okay, chief apologist, well done. Check in the mail. Just kidding. And finally, from the mailbag, we got a number of pieces of email in the last couple of weeks about the International Space Station and our reporting about the deorbiting of it. SpaceX, of course, has been granted an $870 million contract to build a booster stage that will burn up. It's not intended to survive re-entry, to push the space station down out of orbit and into presumably Point Nemo out in the Pacific, which is where you like to dump stuff that's hurtling out of the sky. A lot of people, a lot of you lovely listeners, are a little disgruntled by this, and the general feeling, which is understandable, is, look, we spent a couple $100 billion building this thing, primarily the U.S. How how about we use it for something else? So everything has been pitched from repurposing the modules around the moon or using them for spacecraft or selling them to private industry to sending the ISS out to a graveyard orbit so you could tear pieces off it and smelt them into other kinds of things that you could use in space. Now, there is some logic in that last idea, which is you spend a lot of money to get all this mass up into orbit. If we had manufacturing facilities out there that could use that as feedstock, that'd be great. It's going to be a fair number of years before that happens. So at this point, it doesn't really make sense. And let's not forget, when NASA's looking at budgets and expenditures, everything is gone through with a fine-tooth comb. And if it isn't going to be relevant within a couple of years, it's probably, unless it's a long duration. If you're talking about a robotic probe that's got an 8-year cruise out to Jupiter, for instance, that's one thing. But for this kind of stuff where it might maybe sort of kind of make sense to do it in the future, it kind of doesn't have a chance because Congress is watching every penny.
Do we have
that's
a
something
date yet
China
for
can
when,
afford to do.
Do we have a date yet for when they plan to actually deorbit it?
2030, 2031, somewhere in there.
So 50-50 Starliner will still be docked at that point. It might be
You're evil. Yes, the vines will burn first.
Now we know why it's still docked there. They're gonna.
Oh dear. But there was a big paper released by NASA. There is still some discussion, apparently, about private industry possibly intervening. But the space station's old. You'd have to build things that could dock and work with it, because if the Russians remove their modules, which they still haven't been clear about whether they will or not, that's the power and propulsion unit, and so you'd have to spend an awful lot of money building something to work with it and to interface with late 80s, early 90s technology. So I guess this is a long roundabout way of saying I think NASA probably did a pretty good job on their paper that evaluated these options, but we'll see. Mm-hmm. All right. We will be right back in just a moment with our guests, Jason and Alina. Stand by. And we are here now with Alina Kiessling and Jason Rhodes, who are both, I am told, research scientists and astrophysics at NASA's Jet Propulsion Laboratory. Thank you for joining us today. Appreciate it.
Thanks for having us.
Thank you so much.
So, because you're kind of unique in the industry, at least to my knowledge, can we get a little bit of your origin story, both as scientists and as a couple? Because this isn't something you run into every day, and it must make for really interesting dinner table conversation.
Well, I'm happy to talk a little bit about my origin as a scientist. So when I was a little kid growing up in Australia, my parents used to take us camping in the outback, and we went to an opal mining community. And when I was about 7 years old, I was digging through the cliffs, and I found a fossilized dinosaur bone that had some opal on it. And it was just so exciting and so fascinating. It really made me passionate about understanding origins of the Earth. And that's what I decided I wanted to do with my life, to become a paleontologist. But then when I went to high school, I realized I was thinking way too small, and that I actually was passionate about the origins of the universe. And so from about the age of 13, I knew that I wanted to do cosmology to understand the origin and evolution of the universe. And I spent my career working toward that. I did a PhD at the University of Edinburgh, and then came to JPL as a research scientist, which is really fantastic. And that's where I first met Jason. So I'll let Jason talk a little bit about his background, and then we can talk about how we connected.
Yeah, so I don't have sort of a eureka moment like finding an opal in the Australian outback, but since I was a little kid, I've always been fascinated by science and space, and I read all the science fiction I could and all the science I could all the way up through high school. And as soon as I went to college, I knew that I wanted to study the universe. And when I was starting to go to college, we thought that the biggest component of the universe was dark matter. And so I decided I want to study dark matter. And as I moved from college to to graduate school after going to university, that was about the time that we began to understand that the universe was actually dominated by dark energy. And so I sort of shifted my focus towards the end of grad school and said, okay, I want to study the biggest thing in the universe, and that's dark energy. And so I've made a career out of studying both dark matter and dark energy. And that's what brought Alina and I together. So maybe I'll let her tell how we first met.
So when I was studying in Australia in about 2006, I knew that I was coming to the US to go to a meeting, and it was in Pasadena. And so I looked up everybody who was working in Pasadena in the area of research that I was interested in, and I sent them all emails. And Jason was one of them. And so Jason was kind enough to agree to meet me and to talk about the cosmology and dark matter and dark energy. And so we met in 2006 for the first time, and we became friends. And then I was doing my PhD at the University of Edinburgh, and we remained friends until I came and I started a postdoctoral fellowship at the Jet Propulsion Laboratory. And so while I was at JPL, Jason and I continued spending time together until after about a year, he said to me one day, you know, maybe we should start a relationship.
Maybe we should formalize this, right?
maybe we should do this. And to which I was like, oh, I'm not sure about this. And so he quietly convinced me over the course of a couple of weeks, and the rest is history. We got married in 2014, and everything has been wonderful since then. We now have a 3-year-old, and we're both continuing to work on the same telescopes, and it's been a really wonderful partnership.
Jason, you sneaky devil, you.
Yes. We originally met on the steps of the astronomy department at Caltech. And the reason was Alina was visiting over a weekend. And so I couldn't get her into JPL. And in fact, I couldn't even get her into the building until I went out to meet her on the steps. And fast forward, and we'd been dating a year after she came to JPL, and we were out at a party. And I said, oh, I forgot something at my office at Caltech. We've got to go there on the way home. And she was very annoyed, said, oh, it's the weekend. Why do you have to go to your office on the way home? And so we got to those steps, and she was actually quite cranky with me that I drug her to the office over the weekend. And I got down on one knee and I said, hey, this is where we first met. And I pulled out the ring, and she says, oh, wow. Okay. And she agreed to marry me.
I'm not cranky anymore. Oh, good.
Yeah, agreed that I had done actually a good thing on that weekend rather than making it an annoying weekend.
Okay, so question, given how you met and everything, in that first year, let's say you were sitting over, having a conversation in the JPL cafeteria or something, did you ever have any arguments about what science fiction you read?
Oh, that's a good question.
Or watched?
I think that we're fairly compatible on science fiction. I think other areas of media we might be less compatible on, but we're fairly compatible in science fiction.
Other areas of media. Now that sounds intriguing. Is The Bachelorette in here somewhere or what?
No. I think we have different comedy likes and dislikes.
Yeah, I'd say that's the only place where we disagree on what makes a really funny movie. But for science fiction, we've been very compatible, and we want to see the same movies. And one of us will sometimes read a book and say, hey, you would like this. And so we share books as well. And so I think that's one of the things that's made us compatible. We work together, but there has to be a life outside of work as well.
Yeah.
So I have to ask, because whenever I think dark matter and dark energy in fiction, I think Stephen Baxter. But who is the shared favorite author that you guys have, or do you have one?
That's a really good question too. I'm not sure whether we have a shared favorite, but we both really enjoyed the Bob universe books.
Oh, Dennis E. Taylor.
Dennis E. Taylor.
Yeah, he's a friend. To mention, they all love it. Okay.
Oh yeah, that's probably. And with those, we didn't actually read them. We listened to them on audiobooks, and the narrator is just fantastic in those books, and it adds a lot to those books. And we also have enjoyed both reading and listening to audiobooks of Andy Weir's books, and we read his Project Hail Mary book, or listened to it on a long road trip once, and we actually got to meet him once in person. That was a lot of fun too, because he's probably the closest to science fiction writer to understanding how scientists really work in recent history. And then we both really love a lot of the same authors, and so it's fun to share the books.
Oh, it's just a most amusing coincidence. There's this conference that Rod and I were both at just over Memorial Day, and on the way there, on the flight back, I was alpha reading Dennis E. Taylor's most recent new book that should be coming out sometime in the fall. He'll be tickled to hear you guys love the show. So,
That's
we
really
can't
cool.
wait.
We will definitely listen to that.
Alpha reading. That's a new one by me. I haven't heard that.
Or beta reading.
It's like, it's like a galley. Yeah. All right, Isaac, why don't you kick off with the dark matter or dark energy question, since you know more about it than me and most of the planet.
Most of the universe. But we've I guess it's been almost a century now since Fritz Zwicky first started noticing that there was a very mismatch in terms of how much dark matter there was, or how much matter there was versus what we could see. And we had that kind of overlap of dark matter and dark energy in people's minds, mostly because they kind of make up most of the universe, we're told. But they are not too related in many ways that we can tell. How do you use dark matter to tell us more about dark energy and the structure of the universe? So how does that get taken care of by Euclid or by Roman mission?
Wow, that's a really big question. So maybe I can start, and then Jason can follow on. So about 5% of the universe is made up of normal matter. That's the stuff that you understand, that's stars and planets, people, gas and dust. But then the other 95% of the universe is made up of dark matter and dark energy. So as you said, most of the universe is made up by these mysterious components. And so back in, I think it was the 1930s, you mentioned Fritz Zwicky was looking at galaxies and how they move relative to each other, and really realized that that there had to be some kind of unseen component of matter that was causing them to move the way that they were. And he coined the term dark matter. And then we move forward to about the 60s and 70s, when Vera Rubin was looking at galaxies. And she was looking at the stars in the galaxies and how they rotate around the center, how fast they're moving as they're rotating. And so the stars in the center of the galaxy, you would expect to be moving much faster than the stars at the outskirts of the galaxy. But what she actually measured was that the stars at the outside were moving at the same velocity as the stars in the center. This is only possible if you've got a huge unseen matter component that's gravitationally holding the stars there. And so that was really the first evidence that scientists had for what we now call dark matter. And it was really well received by the community. And we now have even a telescope named after Vera Rubin, who's got a primary goal of investigating the dark matter and dark energy in the universe. And I might let Jason take over to talk a little bit about dark energy.
Yeah, as you said, dark matter and dark energy are often conflated with each other in people's minds, but they're very different things. So dark matter interacts only with gravity. So it tends to pull things together, cause galaxies to stay together and clusters of galaxies to stay together. But dark matter is the name we give to our ignorance of what's causing the universe to expand faster and faster. So that's pushing the entire universe apart, this dark energy. So there's an interplay between the attractive force of gravity, which is mostly acting on the dark matter, and the repulsive nature of the dark energy. So if we look at how structures in the universe form and evolve, and by structures, I mean if we look at galaxies and clusters of galaxies and how those galaxies are interacting and positioning themselves with respect to each other, and how that evolves over time, over billions of years, that's given by an interplay between the gravity pulling things together, the dark matter, and the repulsive nature of the dark energy. So by looking at the positions and shapes and motions of galaxies, we can learn a lot about both dark matter and dark energy.
Okay, so let me jump in with the layperson question here. Because having grown up during the era of the first Star Trek and the original Lost in Space, which I won't make any great claims for, but it was a fun thing for a kid. This dark matter sounds kind of like antimatter, which is dangerous. But I gather from what you're both saying that there's nothing dangerous about dark energy or dark matter. It just sounds dangerous. Although you did call it repulsive. Yeah.
So the dark energy is repulsive, and you say there's nothing dangerous about it. But depending on the strength of dark energy, our universe has a few different ways it might evolve in the future. And given what we know about dark energy now, we think that the evolution of the universe is that the universe continues to expand and push things further and further away until really all the galaxies out there in the universe have been pushed so far away that we can't see them. And so we can only see the stars in our own galaxy. And looking at the universe, it becomes a very lonely place with our galaxy still gravitationally bound, but us not able to see the rest of the universe. And in the past, this very lonely universe where we can't see very much, I've said to NASA or other agencies, I've said, you really got to fund us to study these galaxies now, because eventually they'll be so far away we won't be able to study them. And of course they say, when does that happen? I say, billions of years, whatever. And so it's not a compelling reason to fund my research now, but it does give us pause to think about what the future of the universe looks like and whether it's a very lonely universe. Now, if dark energy is significantly stronger than we think it is today, we actually have a much more violent fate of the universe, in that the universe will eventually be pulled apart. So the galaxy, our galaxy, the stars won't even stay bound. They'll be pushed apart. And finally, in the last stages of the universe, planets and even atoms will be ripped apart as the universe expands faster and faster. So we don't currently think that that's the fate of the universe, but it's always possible as we learn more about dark energy. But we don't think dark matter is dangerous in the sense that, if you have antimatter and matter colliding, there'll be a huge explosion. In fact, we think that the dark matter doesn't really interact with normal matter except through gravity. So there's no violent explosion that we think is going to happen. And in fact, that's why dark matter is so challenging to study, is because it only interacts with gravity, not even with light. So it doesn't give off or absorb light. So we can't see it with the normal types of observations that allow us to see galaxies.
And something to take into consideration is that without the dark matter and dark energy in the universe, it wouldn't look the way that it does today, and very likely we wouldn't even exist. So we've got a lot to thank dark matter and dark energy for helping the universe to appear the way that it does today, and for really contributing to our own existence.
Well, Jason, with my experience with both NASA and the federal government, I want to laud you for thinking well ahead in your research funding requests. I think that's very, very visionary of you. We're going to take a quick break and we'll be right back. So don't be repulsed anywhere. Stand by.
So we've been hearing a lot about a cosmological crisis of late, where there's kind of a mismatching of results about how fast the universe might be expanding or accelerating. And you were just talking about the Big Rip a moment ago. And when I was a kid, Big Crunch was a nice option for gravity pulling things back together. Could you kind of explain where that crisis is coming from and what Hubble tension is?
Yes. So there's what we call a crisis or tension. And what that tension means is it's a tension between results we see by studying the very early universe and studying the later universe. And by very early universe, I mean the cosmic microwave background radiation, which we see, which comes from about 300,000 years after the Big Bang. And that Big Bang, the beginning of the universe, occurred about 13.7 billion years ago. So we have excellent measurements of this cosmic microwave background radiation. So we think we understand the status of the universe around that time. And then more recently, we have measurements of the last half of the history of the universe through studying galaxies, the positions of galaxies, the shapes of galaxies, and the motions of galaxies. Now, if we take what we know about the early universe and what we think physics would do to that universe and play that movie forward, it's not quite what we see in the later universe now. So there's a couple of possible explanations for this. It could mean that our understanding of the early universe is somehow flawed. We've made some mistakes in our measurements or our interpretation. And we think that's probably not true because we've got such good measurements at that time. It could also mean that there's some problem with our measurements of the later universe. There's some systematic effects in our telescopes or the way we're analyzing the data that mean that's incorrect. Or it could mean that our understanding of the physics that takes us from the early universe to the late universe is incorrect or incomplete. And that third option is sort of the most exciting for scientists, because then we have a time when we say, we need new physics, we need to develop new theories, we need new ways of explaining the universe. And we live in a really exciting time because just over a year ago, the European Space Agency's Euclid mission launched. And Alina and I are both scientists working on this Euclid mission. And it's the first mission that's going to gather a whole bunch of data that's going to really transform our measurements of the later half of the universe. So we think with data from Euclid and the Rubin telescope on the ground and the upcoming Roman telescope from NASA in space, all these telescopes are going to provide us with a huge amount of data that will tell us if our later universe measurements are somehow flawed or incomplete, or if we need new physics to explain the evolution of the universe. Now, as a scientist, I need to keep an open mind about what the eventual explanation is. But again, for me, the most exciting would be is if we live in a time where the missions and the data we're collecting from those missions provide us information that tells us we need new physics to explain the universe. That would be really, really exciting.
Great.
So when you say new physics, is this to imply necessarily just something that hasn't been discovered yet? Or does this also possibly imply that physics changes across time and space since the early universe, if that makes sense?
So one of the assumptions we make is that the laws of physics and the constants of physics don't evolve over time, but that's an assumption we're making. And it could be that there's subtle evolution in the laws of physics over time. And what we do now is we have a sort of explanation for how we think dark energy behaves. And it's the simplest explanation. We call it Einstein's cosmological constant. But the behavior of dark energy could be much more complex than is encapsulated in the math behind this cosmological constant. And that's where the new physics could come in, is in a more complicated behavior of dark energy. Or another option is we're using a 100-year-old theory of gravity, Einstein's theory of general relativity, to describe gravity and how gravity helps the universe evolve. But if that theory itself requires some small modifications, we have a new theory of gravity that could help explain some of these observations. So there are lots of ways that this new physics could come in. And again, that's why we're living in a really exciting time, because we're taking the data right now with Euclid every day that's going to allow us hopefully to answer these questions.
To kind of go back to that, you just kind of brought up MOND, or modified Newtonian dynamics. We said earlier that dark matter doesn't interact with anything besides gravity. Do we feel that we might still have the option for very weak interactions, such as the weakly interacting massive particles, or are we switching to something else more like machos or primordial black holes as options? What do you see as the most lead candidate right now for dark matter?
Do you want me to take that, Alina?
I think so, yeah.
Okay, all right. So when I say that dark matter doesn't interact with anything except through gravity, that's to the best of our measurements now. And there could still be some very weak interactions and even self-interaction. That is, dark matter particles could weakly interact with themselves. And there's lots of ways we're trying to study that, both with sort of dark matter detectors on the ground here on Earth, trying to detect a dark matter particle. And so far, we have not conclusively done that, but also different measurements that we can make with telescopes like Euclid and Roman and so on, allow us to try to understand the different properties of dark matter particles. We don't think that the dark matter is things like black holes or machos, these massive chunks of dark matter, because we've done experiments that should have detected those and haven't detected those. So there's a lot of different theories of what the dark matter particle are. And when I say it doesn't interact with anything except through gravity, it mostly doesn't, but it might a little bit. And that's one of the things we're trying to study.
If we could switch back to gravity for a moment for dark energy, we were talking about how we might need to be altering that basic Newtonian concept of gravity, or that basic Newton-Einstein version of it. Do you see that more in the cards now from the data we're getting in, or is it just still on the table and we don't really have much to say one way or another if there's going to be a need to change gravity?
So I think at this point, we haven't got results that have convinced us that we need to change the theories that we have now. So there's the standard theory of cosmology, and that's still the theory that is the most favored by scientists today. But that's why we've got all of these experiments that we're doing. So there's Euclid that just launched a year ago, and then there's two other upcoming experiments. There's the Nancy Grace Roman Space Telescope, which NASA's going to launch in a couple of years, and the Vera Rubin Observatory, which I mentioned earlier, which is a ground-based telescope. And so all three of these missions are going to be looking at the dark matter and dark energy and looking at the models of cosmology and investigating them. And I think that while we don't necessarily expect that we're going to need to change the standard model of cosmology, that most scientists are secretly hoping that we find something that pushes us towards looking for new physics or a new understanding, because that's the most exciting outcome, and it keeps us all in the job.
Absolutely. So you would mention the new telescopes. Can you tell us a little bit more about the Roman? What's the new? What's it got compared to, say, the James Webb Space Telescope or Euclid? What's better about it, or compared to Hubble?
So I can start you off there, and then I'll let Jason take over. But the Hubble Space Telescope and the James Webb Space Telescope are really unique and special telescopes, but they have what we call a narrow field of view. So what that means is that they're looking at a small area of the sky, which means they're really fantastic at looking at, distant objects like single galaxies and studying those in really great detail. What's different about the Nancy Grace Roman Space Telescope is that it's going to have a very wide field of view. So it's looking at a very large area of the sky. And so what takes Hubble hundreds of different pointings takes Roman just 2 different pointings. And so we can see, for example, the entire Andromeda galaxy, if we wanted to look at Andromeda, in 2 pointings of Roman, whereas we'd have to look at that with many, many pointings of Hubble. But the purpose of Roman is not to look at individual galaxies in great detail. It's to look at statistical samples of galaxies to understand what's going on over really large swaths of the universe, which helps us understand how galaxies are clustering together over time, because the further away you look, the further back in time you're looking. So we can understand how dark matter and dark energy have been interplaying over time by looking at the clustering of these galaxies. And this gives us a very good understanding of what's going on with the evolution of the universe. And I'll let Jason add something, because Jason's actually the one of the project scientists for the Roman mission.
Well, I think Alina's described it very well. The Roman field of view, due to advances in infrared detectors, that is the cameras we all now have on our cell phone and so on, that Roman field of view is about 100 times larger than the Hubble Space Telescope field of view. And there's several other ways that Roman will be more efficient at observing than Hubble. Hubble, of course, is in Earth orbit, so it goes in and out of sunlight every 90 minutes. And so half of its orbit, there's the sun there, so it can't be observing the distant universe. Whereas Roman is going to be sent to the Earth-Sun Lagrange point 2, which is a sort of stable gravitational point beyond the moon. So it's in this very thermally stable orbit where it can keep the sun behind it. And so it can observe nearly 100% of the time. So all of these efficiencies make the Roman telescope almost 1,000 times more efficient at doing large surveys than the Hubble Space Telescope. And of course, Euclid has an even larger field of view than the Roman Space Telescope and is observing now. The difference between Euclid and Roman is that Roman is a larger space telescope, has a larger mirror than Euclid. So Euclid will look at a wider area of the sky than Roman, but Roman will look deeper. So they're very, very complementary in how we observe different aspects of the universe. And they're, of course, both of them are extremely complementary to something like the James Webb Space Telescope, which is looking at individual objects very, very far away, as Alina said. So we've got this, what I call this golden age now of these telescopes that is really kicking off. And as the Rubin Observatory on the ground and the Roman Observatory in space get launched, we're going to be really inundated with data from all of these telescopes. And when we process and analyze that data from all of these telescopes together, we're going to get the best possible constraints on dark matter, dark energy, and a huge slew of other astrophysical topics.
Wow, well, I feel coincidentally like I'm being inundated with data right now. So we're going to take a short break so I can collect my wits, and we'll be right back. Stand by. So, question for both of you: in the next 10 to 15 years, is there a particular question that you would love to see answered, or a dream research project? If somebody said, "Here, I'm Jeff Bezos. Here's $10 billion. Jump on whatever you want. You know, build an observatory on the far side of the moon, build a starship, do whatever you want." What might that be?
Wow.
Long silence there.
What would we do with unlimited funds? Well, there's actually a mission that is being considered by NASA at the moment. It's called the Habitable Worlds Observatory. And this is an observatory that, while its name suggests that it's going to be looking for habitable planets outside of our solar system, which is an incredibly exciting venture, I think a telescope that's capable of doing that is also capable of doing really phenomenal astrophysics, really deeply understanding all different types of astrophysics. And so I think in order to make this mission happen, maybe we don't need all the money in the world, but it's not a cheap undertaking, and it's technically quite challenging. So it'd be wonderful to get a lot of support if somebody like Jeff Bezos wanted to throw some cash our way.
Okay, I'll draft a memo right now. Yeah. Jason, how about you?
Well, I wrote a paper a couple of years ago with a couple of colleagues that took a different tactic of looking at what future space telescopes would look like. And the tactic I took is I said, okay, we know what the next telescope and maybe the next generation of telescope will look like. But when we're studying galaxies, we're studying the motions of galaxies and the shapes of galaxies and what the colors of light, the spectra of galaxies. With, for instance, Roman or Euclid, we'll study the properties in detail of about 2 billion galaxies. Now, this is a huge number of galaxies, but we think there's around 1 trillion galaxies in the universe. So there's maybe 1,000 times more galaxies than we can study with with Roman or Euclid. So I said, what is the last survey we'd ever need to do of galaxies? What kind of telescope would we need to look at all 1 trillion galaxies in some amount of detail? And so we ran the math, and it's a telescope that's, maybe 200 meters in diameter in space. Now, this is a huge, huge telescope, and it's not something we can build now or in the next decade or, even maybe next few decades, but it's something humanity could aspire to in 100 years or so, because it's not an unimaginably large telescope. It's not a telescope the size of a moon or planet. It's the telescope the size of a couple football fields across. So I'd like to see us thinking big, not just as NASA or other space agencies, but as humanity, and saying, all right, how do we gather all the information that's available to us from the positions and motions of galaxies and put that together to answer every question in astronomy that can be answered by looking at galaxies? And how do we exhaust all the information that's available to us in the universe? And what would the next steps be to understanding the universe? Because every time we open up a new observational window, we answer some questions, but we raised more questions than we answered.
So if you had that instrument, the big freaking telescope, do you think you would ever get to the point where you sort of sit back and think, you've seen one bar spiral galaxy, you've seen them all? I mean, is there really that much, do you think, to discover by surveying all the trillion of them? If that makes sense.
If we look at the questions that we have now, it's unlikely that we need to look at all 1 trillion galaxies to answer those questions. But I'm very sure that as we started to look at those galaxies, using our advanced computers that can handle data volumes that large, we would come up with other questions where we'd say, wow, we hadn't seen this, or we hadn't anticipated this. And so what I'm really trying to think about is how can we design a program that would allow us to not just answer the questions we have now, but to answer the questions that come up as we're gathering that data and answering those future questions. So I think to answer your question, no, we don't need to study all trillion galaxies to answer the questions we have now. But if we're capable of studying all trillion galaxies, let's do it.
So
I like that.
You're talking about just the sheer size and scope of some of these things and building huge telescopes. I got to do a fun episode some years back just trying to look at how big you can make a telescope. But we see the scale kind of going up from solar system to galaxy to clusters and superclusters or sheets. And then we have this concept called the end of greatness. I was wondering, do you see any room for that to maybe have some additional structure beyond the supercluster scale? And could you kind of explain to our audience what exactly is the end of greatness?
Do you want to take that, Alina?
Go for it, Jason.
Okay, all right. So when we look at the clustering in the universe, things look what we call hierarchical. That there's structure at the smallest scales, and when we look at our solar system, and there's clustering in our solar system, and there's planets and a big star, and then next biggest scale is a galaxy, and we look at galaxies cluster together, and then the galaxy clusters form superclusters. But once we get to large enough scales, we're looking at appreciable fractions of the universe. And while the actual universe may be infinite, the observable universe, that is the universe in which we could not just observe, but interactions through gravity could propagate to that part, is not infinite. And so there's got to be a largest sort of scale that things can cluster on, that's the size of the universe. So there is a limit to clustering in the universe, just like there's a limit to what we can observe in the universe. What we can observe is not infinite.
That's kind of mind-boggling. Sorry, go ahead, Isaac.
Oh, it's a huge scale. One of the things my audience always says when they see these pictures is this, that it looks so much like a brain at that scale. And a lot of times they'll say, well, it's kind of the way the dark matter and dark energy is set up, that you get these voids and these big long chains. Is that what you're still seeing? Is that with the newer data, is that still emphasizing that kind of scale image of the large voids and the very brain-like appearing nature or tree-like nature of the galaxies?
So what
we do see that. Sorry, you take it, Alina, and maybe you could talk about how we simulate the universe and compare those simulations to the real universe.
Yeah, so I actually like to think of the picture of the universe in dark matter as like a big spider web, because as you mentioned, there are these voids and filaments that are really sort of permeating throughout the large scale structure of the universe, and we see that quite beautifully in these simulations that we do of the universe in computers. And so this is something that I've been working on for a number of years. My PhD was actually in the field of creating these dark matter simulations of the universe. And dark matter is very easy to simulate because it is interacting only through gravity. And so what we're able to do is have lots and lots of dark matter in our computer, and we can propagate that over time, just allowing it to evolve by gravity. And using the current state of cosmology, the way that we think the universe currently is, we can actually reproduce these large-scale structures that we're seeing in the universe today. And this is a very important part of what we're doing to prepare for these upcoming missions. We're making lots and lots of simulations of the universe to really try to understand what it is that we're going to see from these big telescopes. And so, yes, the scientists still believe that that picture that you painted of a brain or a web of large scale structure, and really we're talking about millions and billions of galaxies and up to, you know, 1 trillion. We believe that there's 1 trillion galaxies in the universe today. That's the structure that they continue to maintain through this push and pull of dark matter and dark energy.
You know, I was fascinated by the kid a couple of years ago that sat down and spent, I think, the better part of a year building a model of the solar system in Minecraft. Did you happen to see that?
No, I'd love to see that. Yeah.
Unbelievable. I mean, you know, used a couple of million bricks to do the sun and then shaded the bright side manually. I mean, it was just crazy. So now we can give said young man a new challenge, which is to build a Minecraft model of the universe based on what you're seeing out there. That would be an achievement. That's kind of like an X challenge. Okay, sorry, Isaac, that was a silly one. Go ahead.
Well, mine might be just as silly. When we were mentioning that you could see Andromeda with just two photographs of it at once, and Andromeda is one of those very few distant night sky objects you can actually see as more than just one little pixel without having to use a telescope. And it's trying to appreciate, well, it's just one little pixel in the sky, but it's so huge compared to everything else. There's millions of galaxies in that shot. Coming to the more local scale, though, one of our other objects we can see is planets at the local scale, though, more than a pixel. Do you see any use for Euclid or for the Roman mission to be able to help us with our exoplanet hunts at all?
So I can take that. So one of Roman's primary goals is to do an exoplanet search with a technique called microlensing. And what you do in a microlensing survey is you stare at the center of our galaxy and look at a field of stars, and you wait as those stars move for a chance superposition of two stars. And when one star goes behind another one, this gravitational lensing technique will make that star blink brighter for just a brief period of time. And if that star that is causing that lensing event also has a planet, there's a secondary spike for that planet. And so by looking at these dense fields of stars over the course of years, every 15 minutes or so, we take an image and we compare. We hope to, with Roman, find literally thousands of additional planets that we have not found before. And right now we've discovered about 5,500 or so exoplanets in the past 30 or so years. And so thousands more will be discovered by Roman. Additionally, Roman, in addition to this very wide field camera, Roman has another instrument called the coronagraph instrument. And that's being built, or was built, right here at JPL. And just a few months ago, it was shipped off to NASA's Goddard Space Flight Center, where it's awaiting integration into the Roman telescope. This coronagraph instrument is an optical instrument that places really a disk over a star. And by placing a disk over the star, you block light from the star, and then you're able to see the very faint exoplanets that are orbiting that star. And so we won't discover thousands of exoplanets with this Roman coronagraph, but what we will be able to do is look at a handful of exoplanets in exquisite detail. Whereas most exoplanets that we've discovered, we know that they're there, but we don't actually see them. We see them through some interaction with their star, the star blinking or the star going dim for a second. But these planets with the coronagraph on Roman will be able to see those planets and take spectra of them and understand the characteristics of the planets. And that Roman coronagraph is putting to use a number of new technologies together for the first time to be able to provide a huge improvement in the contrast ratio, the ratio of how dim the star is compared to how bright the planet is. And by using those same technologies together on a future observatory, the one Alina talked about, the Habitable Worlds Observatory, we think that we'll be able to build a coronagraph that could look at Earth-like planets around sun-like stars when those planets are in the habitable zone and possibly look for signs of life on those planets. So it's within our technological grasp in the next 2 decades to be able to potentially detect life on an exoplanet. And that's a really exciting time to be living in for an astronomer, because that would be a discovery that doesn't just resonate with astronomy. It would resonate philosophically with hopefully everyone in the world to know that we are not alone in the universe.
I have to ask, when we say signs of life, are we thinking biosignatures or atmospheric telltales or technosignatures, or what kind of signatures are you anticipating?
Alina, you want to take that one?
So I think what we're expecting with the spectroscopy from something like the Roman coronagraph or a future iteration on something like the Habitable Worlds Observatory is really biosignatures. So we're looking for examples of methane and ozone and oxygen that really demonstrate potential signs of life. And we have to be very careful with these analyses, because there are false positives that we can have, things that look like they could be biologically generated that aren't. And there's an enormous amount of work going on at the moment, really trying to understand how to interpret these signals that we may be getting from spectra of these exoplanets. But I think that's really the primary path that we're looking to at the moment, because I think the easiest expectation is that life that we're searching for is probably not going to be intelligent and putting out those technosignatures, as you mentioned. So technosignatures being like radio communication or other types of laser optical communication. We're just hoping to be able to identify it through the biological signs. And imagine what Earth would have looked like when we were looking at it millions of years ago. So before we had the technological advancements and the atmosphere as it looks today.
Awesome.
So this is a question for both of you, but I think we could start with Alina. If I'm talking to, as we kind of are, a group of young women and young men that are interested in this field, would you call this a growth area, and what advice would you give them for moving into it?
So is the field that you're talking about exoplanet research or just astrophysics in general?
Everything you guys do.
Everything. So in my opinion, astrophysics is something that will persist throughout humanity. And one of the things that I have found most wonderful about the telescopes that have been launched, or the ground-based telescopes, is that their primary purpose for being built has never been the most interesting or the most exciting thing that they've ultimately discovered. And so if you imagine the science that was imagined when the Hubble Space Telescope was put up, that no longer sits as the most exciting things that Hubble discovered and the most wonderful things that have captured the imagination of society, that encouraged more and more people to get involved in science and to care about science. So I believe that astrophysics will continue to be an area where you can discover, you can share the wonder of what you're learning with the world in a way that people can really identify with and resonate with. And the world really just needs more scientists. I think scientists do make the world a better place.
I can add maybe more practical advice in the way that I see the field going. And that is, I said that we've discovered 5,000 exoplanets, but there's going to be thousands more with Roman and with Euclid and Roman. We're taking the number of galaxies that a survey looks at from thousands or even millions to billions. So this is going to require this huge number of objects, whether they are exoplanets or galaxies. It's going to require new techniques in machine learning and artificial intelligence to process and understand that data, because we can no longer look at each individual object by eye ourselves and do a detailed analysis. So we're going to rely on computers learning how to do that. And so one of the real growth areas I see in astrophysics is for people who have those skills in developing machine learning and artificial intelligence techniques to bring them to bear on astrophysics problems. And one of the things that's really great and satisfying for me is as we bring up grad students or postdocs that work for me, some of them go on to work in astronomy, but others take the techniques that they've used and they go on and work in industry or other science areas or other areas of the economy. And having those skills in machine learning and artificial intelligence is going to be a big part of the world economy going forward. So I see astrophysics as training people to think in ways that are going to benefit us, not just in understanding the universe, but in having a better and more productive future for all of society.
Well, that's pretty cool. Now, we do have to take one more break, and then I'll be back for my last question for Alina. So a little birdie named Rob Banning told me last night, Alina, that you and he share a passion for archaeology. Can you just tell us a little bit about that?
Oh, for paleontology, I think I think I started telling you this story at the beginning. So this was a story about how I found the fossilized dinosaur bone with the opal on it, and how it just really ignited my absolute passion for understanding origins, and that led to me wanting to understand the origin and evolution of the universe. So I really I think I can thank paleontology as being the first step toward my career as a cosmologist.
That's pretty cool. So where do you guys go on vacations? If that's part of it.
Yeah, so we sort of alternate. We used to be somewhat adventurous travelers, and now we have a 3-year-old. And so when we go to the same meeting, we often bring that 3-year-old with us. We were in Rome, Italy about 10 years ago, and I'm a history buff. So we took a bunch of tours of the Vatican and the Roman Forum, and it was fantastic. And then we were 2 weeks ago at the annual Euclid meeting in Rome. And so we took a couple of extra days with our 3-year-old, and she was very insistent. I want to go to the park and go on the swings. So it wasn't the same sort of visit to Rome, but one of the places we've found that we all sort of like is going to the beach in Hawaii. We enjoy it. We enjoy the time off, and our now 3-year-old loves the beach and the pool. And so we're hoping that she's sort of intellectually curious and adventurous like us. So in 10 years, when she's a little older, we can drag her along to our work meetings and see parts of the world that she might not otherwise be able to see.
I guess you're a little less likely to see the Pope hanging out at the swing set by the beach than at the Vatican.
Probably.
Oh,
yes.
Well, thank you everyone for joining us today for episode 118 of This Week in Space, Understanding the Darkness. Please don't forget to check out Isaac Arthur's YouTube channel, Science and Futurism with Isaac Arthur, where you can watch over 700 hard science videos. I've watched a handful of those, but I've really enjoyed the ones I have because these are deep dives into subjects like what we've talked about today. And of course, you can always check out the National Space Society at nss.org. Both are good places to satisfy your spaceflight cravings, along with whatever website Alina and Jason are going to tell us to check out for their work. Take your pick.
Well, I would say for the science, understanding the science, Wikipedia is a great start to learn about dark matter and dark energy. And if you want to learn more about the missions that we work on, just Googling European Space Agency Euclid or NASA Roman mission. Both ESA, European Space Agency, and NASA do a great job of explaining the mission in terms of both the science and the really amazing hardware that's going to enable this science, the telescopes and the detectors and so on.
Yeah, this is a pretty incredible time for space telescopes and the science that relates to them, isn't it? And there's so much stuff coming along, and we haven't even talked about some of the big space telescope projects that are out 10 and 20 years, which are
it's like a really, post-web revolution. You know?
Yeah, really, really amazing.
Waiting so long for that to get up there. Now we've just got a wonderful surplus of them.
All right. Speaking of revolutions, please, listeners, don't forget to drop us a line at twis@twit.tv. That's TWIS at twit.tv. We always welcome your comments, suggestions, and ideas. And don't forget to subscribe to and like our show on the podcast delivery venue of your choice, because we live and die by your thumbs up and reviews and so forth. Finally, don't forget you can get all the great programming on with video streams and everything else on the Twit Network ad-free at Club Twit for as little as $7 a month. And there'll even be some extras on there. Maybe you'll even catch some of Isaac's off-camera jokes, because those are keepers. You can also follow the Twit Tech Podcast Network at Twit on Twitter and on Facebook, and twit.tv on Instagram. Thank you very much, everybody, and we'll see you next week. Bye-bye.